Okay, so get ready to flex those brain muscles a bit, because today we're taking a deep dive into process algebra. Now, I know that might sound a little intimidating, but trust me, stick with me. It's actually all about, finding these like really elegant solutions to a pretty basic question. How can we know for sure that two things that maybe look totally different, how can we be sure they actually behave the same way?
Yeah, it's kind of like that whole thing about judging a book by its cover, right?
Yeah.
Like we want to know deep down if two systems or processes, whatever you want to call them, if they're really truly interchangeable, even
Yeah.
if like the way they're built is totally different.
Exactly. Just because two things look different on the outside doesn't mean they can't get you to the same place, right? Achieve the same results. And that's where I guess this idea of equivalence comes in. Yeah.
Exactly, yeah. But you're right. It's not as simple as it might seem at first. The stuff we've been looking at, it dives into all these different like levels of equivalence, and they each have their own, strengths and weaknesses, things they're good at, things they're not so good at. But let's start with the most basic level, the kind of foundation, and that's what they call transition system equivalence.
Okay. Yeah. Let's break that down a bit. What are we actually talking about when we say that?
So picture this. You've got two maps,
Huh.
right? And they both show the exact same route, identical routes. They might look exactly the same on paper, but this level, this transition system equivalence, it's often way too like granular, way too much detail. You know what I mean? Not that useful in the real world. It's kind of like
Serious, yeah.
it's like saying two people took the exact same route on a road trip, but one stopped for gas, maybe grabbed a snack, took their time. The other one just drove straight through, no stops.
Yeah.
Technically, same route, but a totally different experience, right?
For sure. So it's like saying, oh, all maps are the same because they all like help you navigate. But we all know some maps have way more detail, right? Some are just like big picture. Others, they show you every little back road. So if that's like the most basic level, what's the next level of equivalence we're looking at here?
Right, so that brings us to what they call string equivalence. And this one, it kind of shifts the focus. Instead of looking at every little twist and turn, every little detail, it's more about the overall picture of like what actions can a process actually take, Think of it like if you were writing down directions, it's less about turn left here, turn right there, and more about just listing out all the possibilities like left turn, right turn, go straight. If two processes have the same exact list of potential actions, then boom, they're considered string equivalent. Makes sense.
Okay, so instead of obsessing over every little step, every little choice, we're kind of zooming out, looking at the big picture of what's even possible in the first place, regardless of the order things happen in.
You got it. You're getting it. However, even though it sounds good, string equivalence has a couple of pretty big flaws, honestly. Like, first of all, it can't tell the difference. It can't tell if a process, like, eventually stops or if it just gets stuck, going in a circle forever, an infinite loop, as they say. And second, it really, really has trouble dealing with randomness, or choices within a process. It's like comparing two recipes, right? One recipe might say very specifically bake for 30 minutes, but then the other recipe says bake until golden brown. Now, string equivalence, it would just see those as the same because they both involve baking, right?
Yeah.
But the outcome, that could be wildly different.
Okay, I see what you're saying. Things are starting to get a little tricky. So we need something, obviously, a little more, I don't know, nuanced, right? A more sophisticated approach to tell if things are truly equivalent.
Exactly. You're on the right track. And that brings us to what we call strong equivalence. Now, this is all about finding a perfect match, like step by step, between the actions of two processes. Imagine it's like you're drawing lines, right, between each action in one process, connecting it to its counterpart in the other process. And if you can connect everything perfectly, no loose ends, nothing left over, then those two processes, they're considered strongly equivalent.
Okay, I think I'm following. So it's less about the overall possibilities and more about the specific order, the sequence of actions. Like they have to mirror each other perfectly step by step for it to count as strong equivalence.
Precisely.
Yeah.
You got it. It's like, imagine those two people, again, navigating that maze, right? They each take a different path, but every single step of the way, they're mirroring each other's moves. If one of them hits a dead end, well, the other one, they're going to hit a dead end too. And this whole idea, it's called bissimulation, fancy word, but it's really the heart, the core concept behind strong equivalence. And the really cool thing about this is it actually solves those issues that we were talking about with string equivalence. Like
Yeah.
you can tell if one process stops while the other keeps going, and it handles randomness like a champ. No problem.
Now that is what I call some elegant problem solving. But I gotta imagine there's always a catch, isn't there?
You're catching on quick.
Right.
You're absolutely right. Even strong equivalence, even with that elegant simulation, it does have its limits. And it often gets tripped up by, get this, by what we call tau actions.
Tau action. Okay, you're gonna have to explain that one.
All right, so think of tau actions like this. They're like these hidden internal actions that a process might be doing, but they don't actually affect the overall outcome. It's like if you were taking a road trip, right? And you decide to take a little detour. Maybe you want to see a landmark or something. But that detour, it takes you right back to the same spot on the main road. You didn't change your destination, didn't really get sidetracked, but you had a little complexity, right? A little detour that, in the end, didn't really change where you end up.
Okay, so it's like those times you rearrange all the furniture in your living room, right? You spend all this time moving stuff around, but then you put everything back exactly where it was. Technically, you did something, you took action, but the end result, the final state, is the same.
That's a great way to put it. You got it. And these seemingly insignificant little tau actions, these little detours, they can really mess with strong equivalence because remember, it's so laser focused on matching every single action, every little step, even the hidden ones.
Okay, I'm starting to see the problem here. So if strong equivalence can't always handle these stealthy little tau actions, what do we do? How do we deal with that?
Well, that's where things get even more interesting. That's where we dive into the world of, get this, weak equivalence. But before we do that.
Okay, so just to recap, we're wrestling with this idea that even strong equivalence, which seems pretty, rigorous with that whole simulation thing, even that can get thrown off by those sneaky little tau actions, those detours that ultimately don't change where you end up. So what's the solution here? Do we just give up, throw in the towel?
Not at all. This is where, you see how clever computer scientists can be. There's this pioneer in the field, Robin Milner, brilliant guy, and he came up with a pretty elegant solution. Weak equivalence. It's kind of like, imagine strong equivalence, right? But this time it's wearing like noise-canceling headphones. It's filtering out all those distracting tau actions so they don't mess up the comparison.
Oh, I like that. That's a great analogy. It's like focusing on the actual signal and ignoring all the background noise. So what you're saying is weak equivalence is all about honing in on the actions that really matter, the ones an outsider, like an observer, would actually see and care about, the actions that have a real tangible impact on the outcome.
Exactly. You got it. It's about cutting through the clutter, getting to the heart of the matter. So weak equivalence, it basically takes those sequences of hidden actions, those internal tau actions, and it just collapses them gracefully to a single step. So instead of getting bogged down in all those little internal details, those detours, it's like we just fast forward through the boring parts of a movie, right?
Yeah.
And get to the good stuff.
Okay, yeah, that makes a lot of sense. So, like, if a process goes on this whole internal journey, takes a bunch of steps, but ultimately ends up right back where it started, like our furniture rearranging example, weak equivalence, just sees it as one action, rearranged and then unrearranged. The detour might have happened, but who cares? It didn't change the final result.
Exactly. You've got it. You're really getting this. Now,
Yeah.
I do have to say, as awesome as this approach is, it's not, a magic bullet. It's not perfect. Yeah. Even weak equivalence has its limitations. The stuff we've been reading, it points out that it can run into some trouble, especially when you're dealing with processes that involve a lot of randomness, or what we call non-determinism in computer science jargon.
Okay. Can you elaborate on that a little? Like, what kind of scenarios are we talking about here? Give me an example.
All right, picture this. Remember those choose your own adventure books? Those were the best, right? Well, weak equivalence might have a bit of a tough time comparing two of those stories where the choices you make, those branch points, those points of non-determinism, if they lead to wildly different outcomes, even if some of the paths overlap along the way, you see. That inherent randomness, that element of choice, it adds a whole other layer of complexity.
That's a really, really good way to illustrate it. So even though both books have those choices, and some choices might lead to similar points, maybe even the same page at some point, the overall possibilities, the range of where those stories could go, that could be totally different. It's not just about, like, having choices. It's about how much impact those choices have on the whole trajectory of the story.
You've got it, 100%. And it's really important to remember, we're not saying that weak equivalence is here to replace strong equivalence altogether. It's not like one is better than the other. They each have their own strengths, their own, domains where they excel. In fact, when there are no tau actions involved, guess what? They basically become the same thing. It's only when those sneaky little hidden actions come into play that weak equivalence really shines, because it gives us this much more effective way to compare and really understand what's going on with these processes.
Okay, that makes sense. So it's like having different tools in your toolbox, right? You wouldn't use a hammer to try to tighten a screw, or at least it wouldn't be the best tool for the job. Each type of equivalence, it has its own specific uses, its own strengths, depending on the kind of processes we're dealing with.
Exactly. A perfect analogy. And, the stuff we've been going through, it actually goes into some really fascinating, although I'll admit, kind of technical details about how these different types of equivalents are used in practice. Like, for example, in verifying that a piece of software is correct, that it does what it's supposed to do, or in designing really robust communication protocols. These concepts are critical.
See, now that sounds like a whole other deep dive waiting to happen. But before we get ahead of ourselves, can we just bring it back to the big picture for a second? Like, for all of us out here who aren't, computer scientists, what's the takeaway here? Why should we even care about all these different flavors of equivalence in our everyday lives?
That's the million-dollar question, right? And it gets to the heart of why this whole topic is so fascinating, because at its core, understanding these different types of equivalence, it actually helps us think about, to reason about, all these complex systems we deal with in a much more, sophisticated way, a more nuanced way. It's about having the tools to make sure these systems behave the way we expect them to.
So it's kind of like having that confidence that the systems we rely on every day, whether it's a piece of software or just an appliance in our home, it's about trusting that they're reliable, that they're not going to go haywire and do something completely unexpected.
Precisely. That's a great way to put it. It's that trust, that reliability that matters. It's like, having that confidence that your navigation app, even if it chooses a slightly different route than you were expecting, you still trust that it's going to get you where you need to go. You're trusting the process, even if you don't necessarily see or understand every single step along the way. And that peace of mind, that's priceless, right?
Absolutely. It makes you realize, how much we just take for granted when we say two things are the same, right? Like, we just throw that word around, but there's a whole world of complexity behind that seemingly simple statement. But I have a feeling we're just scratching the surface here, aren't we?
You're definitely picking up on things. You're right. What we've talked about so far, that's really just the foundation. Because one of the things our source material hints at is, it turns out actually figuring out if two processes are equivalent in any of these ways we've been talking about, that can actually get really, really complicated from a computational perspective.
Oh, now that sounds interesting. Tell me more.
So imagine you're trying to figure out if two processes are string equivalent, right? You basically have to compare every single possible combination of actions those processes could take, every single path they could go down. And as those processes get bigger, more complex, more intricate, the number of possible combinations, it just explodes. It's like exponential growth, like trying to compare all the possible routes you could take on a cross-country road trip. The possibilities, they just become overwhelming.
So it's like we're not just talking about a lot of possibilities, we're talking about this explosion of possibilities, a combinatorial explosion, right? And I'm guessing that's not exactly easy for a computer to handle, is it?
You got it. You're exactly right. It's like trying to find, I don't know, how about this? It's like trying to find a single specific grain of sand on an entire beach. Like, it's technically there, right? But to actually find it, you'd have to spend an insane amount of time just searching and searching and searching. And the worst part is, as these systems, these processes, as they get more and more complex, well, the beach, it just keeps getting bigger.
Okay, yeah, that does not sound like a fun task. So what do we do? Are there ways to deal with this? Are people working on solutions?
That's the thing about computer scientists, right? They love a good challenge. So yeah, there are tons of really, really smart people out there who are constantly coming up with more efficient algorithms, better techniques, all to try and manage this complexity. They're finding these super clever ways to navigate that massive beach we were just talking about, but do it in a smarter way, So they're not just randomly digging in the sand. It's like they're inventing a metal detector, but a metal detector that's specifically designed to find that one specific grain of sand.
Okay, now that is impressive. It really shows you, even when we're talking about these super theoretical, kind of abstract ideas, equivalence in process algebra, it's not just living in some ivory tower. There are very real-world consequences, real-world challenges that come with it.
100%. And speaking of real-world stuff, it just occurred to me, we were talking earlier about weak equivalence and how it can sometimes have a hard time with those choose your own adventure type scenarios, those processes where there's randomness involved or to use the fancy term, the non-deterministic operator.
Yeah. Those choose your own adventure books, it seems like weak equivalence just like can't quite wrap its head around those. Can we dig into that a little bit more? Give me another example, maybe.
Of course. So how about this? Let's imagine two vending machines, right?
Yeah.
Okay, the first vending machine, it's very straightforward. You walk up, you see all your options, candy bar, bag of chips, whatever you make your choice, you put your money in, you get your snack. Simple, right?
So far, so good. What about the second vending machine? How's it different?
Okay, so the second vending machine, this one's a little more, shall we say, mysterious. It only has one button. So you walk up, you press the button, and then, here's the thing. Behind the scenes, the vending machine is secretly, randomly deciding whether it's going to give you a candy bar or a bag of chips. You don't get to choose. The machine decides for you.
Okay, I see where you're going with this. So both vending machines, they could ultimately give you the same snacks, but the way they go about it, the decision-making process, that's what's different.
Exactly. You're getting it.
Yeah.
And it's that difference, that hidden randomness in the second vending machine, that's where weak equivalence might get a little confused, you see. Because it sees that both machines can produce a candy bar or a bag of chips, but it doesn't necessarily grasp that crucial difference in timing and the fact that in that second scenario, your choice, your agency, it's taken away.
So even though if you were just observing, just watching these two vending machines, they might seem pretty similar because they both give out snacks. But deep down in their inner workings, in that element of choice versus chance, that's where the difference lies, right? At least when we're talking about equivalence at this level.
Yeah.
It's subtle, but it matters.
100%.
Yeah.
It all comes down to nuance. And, this really highlights how these concepts, equivalence, Bayes simulation, all these things we've been diving into, yeah, they come from this world of theoretical computer science, but they have these really practical implications. Because in the real world, when we're building systems, when we're trying to understand how things work, we have to pay attention not just to the what's the outcome, but also to the how. How did we get there? What were the steps along the way? Those tau actions, those choices, those random events, they all play a part.
Wow, this whole deep dive, it's really like shifted my perspective. I'm looking at sameness in a whole new light. It's definitely not as black and white as I used to think.
And that's what makes it so fascinating, right? This one simple question, are these two things the same? It can send you down this rabbit hole of all these intricate details, all these elegant solutions, all this deep thinking about how things work. It's amazing.
It really is. Well, on that note, as we wrap up our deep dive into the fascinating world of equivalence in process algebra, I want to leave our listeners with a little something to ponder. Think about how you define equivalent behavior in your own life. Is it all about the end result? Or do the specific steps you take along the way, those tau actions, do those matter to you? It's something to think about. And that's it for the deep dive. Thanks for joining us.